Okay, so now let's dive into these logic gates a little bit deeper. So we're going to go down a lower level of abstraction and look at how these gates actually function. So we've already talked about discrete voltages representing 1 and 0. So for example, 0 is 0 volts. That's generally true. And VDD, which is the high voltage, is 1. So for example, it could be 5 volts. We could have, 3.3 volts, 1.1 volt. But some high voltage is considered 1. If we're in a 5 volt system, the highest voltage is considered the 1. If our system is running off 3.3 volts, 3.3 volts is the value considered to be a 1. So we have 0 at 0 volts, and our 1 is 5 volts. What about 4.99 volts? Is that a 1 or a 0, or we call that invalid? Probably I'm close enough, right? Maybe it's a 1. What about 3.2 volts? That's really getting into a gray area. So we have to define what we do for these different values. If we're extremely strict and say, hey, you're either 0 volts 0, 5 volts 1, anything else, and I'm not going to consider you as a valid value, that system's going to have a really hard time working, because getting exact voltage values is pretty tricky, especially given noise in the system. So instead of having just a single value, even though at the abstractest level we say 5 volts is a 1, 0 volts is a 0, we actually allow for a range of voltages to be considered a valid 1 or a valid 0. So we'll use a range of voltages for 1 and 0 instead of just exact values, 5 volts and 0 volts. And we'll have a different range for inputs and outputs to allow for noise. So what is noise? I've used this word a couple times now. What does that mean? Right? Well, you think of everyday life. Noise is you're trying to talk to somebody and the room's really noisy. You're at a restaurant or something, and the signal that you're interested in, the person talking to you, is being corrupted by noise in the system, by other signals. So it's basically anything that degrades the signal of interest. So what are these things in an electrical system? In a digital system, resistance can degrade the voltage levels. The power supply can vary. If you're running off a battery, as that battery goes lower, your power supply, your 5 volts, is going to droop a little bit as different devices demand different values of current. That voltage supply can also vary. Maybe a neighboring wire is pulling up. It could pull that signal up as well, causing noise on the signal of interest. So bunches of reasons for noise. I'm not going to test you on these reasons in this class, but important to know that they exist. And so here's an example of what could happen. A gate, a driver, well, we call it the driver because it's the one outputting the signal. Output's a good 5 volts. We're dealing in a 5 volt system where 5 volts is 1. But maybe there's a really long wire here. It finally gets to its destination. Because of resistance in that long wire, it degrades to 4.5 volts by the time it gets to the receiver or the one receiving that signal. So in this case, the driver is a buffer and the receiver is a buffer. Well, what does it do with that 4.5 volts? Does it say, now my system's going to malfunction because it wasn't 5 volts? Well, we can define a range of values so that 4.5 volts is detected as a 1. And so now this refers to the static discipline. So static discipline, static means stable or staying in a given voltage. It's not changing. We're interested in when it's reached its final value. So static or stasis. And the static discipline says, with logically valid inputs, every circuit must produce logically valid outputs. Okay, let's define logically valid. So that's talking about that range of voltages that we're going to say is valid. And we're going to use this limited range of voltages to represent our discrete values. So we're still using ones and zeros, but we're allowing a little more wiggle room to allow for ranges of voltages instead of just 5 volts and 0 volts, nothing else. Okay, so let's consider this system that we just talked about with our driver and receiver. Our driver is a buffer and our receiver is a buffer. We're interested in the output characteristics of our driver. So we're interested in the signal as it outputs from the driver, and the input characteristics of our receiver, because our receiver is receiving that potentially degraded signal into its inputs. So let's take a look at this. So our driver, ideally, it's high voltage. It's 1. Let's say we're in a 5-volt system, so we'll use 5 volts, and it's 0 is at 0 volts. So here's our ideal system. Our driver outputs 5 volts. It gets to the receiver, and it's all good. That receiver sees 5 volts as its 1, and 0 volts as its 0. And this is an ideal system. Everything works. The driver outputs 5 volts. It goes to the input. It sees it as a 1, or it sends a 0 volts, and the receiver receives that 0 volts as a 0, says, cool, we're all good. But what about the non-ideal case, where the output, the driver outputs, instead of 4.5 volts, maybe it outputs something not quite as good. Maybe it outputs 4.3 volts. Gosh, that wasn't great, but kind of close to 5 volts. So this driver outputs something a little bit less than ideal. Well, as long as the receiver says, hey, you know what? My 1 I'm going to define as, well, should we define it as exactly 4.3 volts? What about for any noise coming onto this wire? Now that doesn't account for any possible noise between when the driver sends the output and the receiver receives it. So instead of making it exactly 4.3, let's make it a little bit larger region. So for example, we could say, I don't know, 3.8 volts. Anything between 3.8 and 5 volts, this receiver will receive as a 1. Okay, so now this system sends the driver sends its kind of degraded output voltage, high output voltage, but the receiver, because it has a larger range, says, hey, that's fine, 4.3 volts, yep, I see that as a 1. Same thing on the low end, on the 0 end. Let's say the driver sends something like 1.5 volts as a 0. That's a degraded 0. It's definitely not 0 volts, but kind of close. As long as the receiver receives something, let's say it receives something at 2.5, anything between 0 and 2.5 volts, it will receive as a 0, this entire range of voltages. Now that 1.5 volts will be sent by the driver and in fact received as a 0 by the receiver. So these values, let's give them some terms. This worst case output value, this 4.3 volts, is the voltage output high. So it's the worst case output high voltage. Voltage output high. The worst case output high voltage. This 1.5 volts is the voltage output low, or the VOL, worst case output low voltage. And then kind of as a corollary, now we have our voltage input high and voltage input low, the worst case input high and low values. And again, we'll notice that these values are not the same. So the output high and the input high are not the same to allow for external noise in the system. So if we take the difference between these two, well, it can send 4.3 volts, this driver. It can have up to, well, 4.3 minus 3.8, 0.5 volts of noise, external noise, and still be detected as a 1 at the input of the receiver. So this is called the noise margin, the high noise margin. So the noise margin high, put it into equation form, is equal to voltage output high minus voltage input high. In this case, it's 4.3 volts minus 3.8 volts is equal to 0.5 volts. So we have 0.5 volts of noise margin, allowing for external noise in the system to degrade the signal. For example, long wires. Similarly, we also have a noise margin on the low end. So here's our noise margin low. Well, as we can see in this case, we have a 1 volt noise margin. The driver can send 1.5 volts. It can degrade by another volt, so get higher in this case. Degrading is making the zero an even worse zero. So it can degrade by 1 volt and still be detected as a zero. So we can turn that into an equation, or write that in equation form. The low noise margin, so for the 0 range, is, well, now we do voltage input low minus voltage output low. In this case is 2.5 minus 1.5 volts. And we have 1 volt of noise margin on the low end, or the 0 end. Okay, so let's review this. Here's a pre-drawn picture of our noise margins. We can have our logic high output range. Here's our 1 for the outputs, our 0 for the output. And in order for our system to work, the range on the receiving end for 1 and 0 has to be bigger, so that we allow for a noise margin both on the low end and on the high end. And when doing these kind of problems, strongly recommend drawing a picture like this. Right? It's easy to flop these and try to remember, is it voltage input high minus voltage output high, or vice versa? If you draw the picture, it's a lot more clear. Okay. And again, just same thing as before. When you do an example, a lot easier to see and make sure you're doing the right thing and not just plugging in a number. You hope it's right. You can verify that it's correct or not. So the power levels VDD has scaled from the 1970s and 80s. We had 5-volt systems, and it's dropped, partially because transistors have gotten smaller, and so to avoid basically burning up these transistors, and also to save power, voltage levels have dropped to 3.3, 2.5, and even lower in recent years. So you have to be careful when connecting chips with different supply voltages that they don't fry one of the chips operating on a lower voltage. And then the tongue-in-cheek statement that chips operate because they contain magic smoke. The proof is that if the magic smoke is let out, the chip stops working. So must be the magic smoke, right? Yeah, maybe not magic smoke, but maybe. Okay, so let's look at some different logic families. And if you're actually buying chips or going to the lab and working with chips, being aware of what logic family is operating is useful to be able to tell whether they will work together. So for example, let's do some examples here. So we have these specifications, the nominal VDD, the input characteristics, input low and high, the input gate, and the output characteristics, output low and high for the gate. So for example, we could do an analysis to say, hey, what if we had a TTL driver, so a chip on one end, driving a low voltage CMOS receiver. Would this work? So we're interested in the output characteristics of our TTL circuit and the input characteristics of our low voltage CMOS or LV CMOS circuit. Where do these numbers come from? Input high, input low, output high. They come from a data sheet. So if you ever use a chip, you can get the data sheet. Often Google it, or it comes with when you order it, and you can read these electrical characteristics. Okay, so let's try this out. So like I said before, best thing to do is to draw these kind of stick diagrams of what we have here. TTL is nominally running at 5 volts, and 0 low voltage CMOS is running, so we could redraw that to be a little bit more accurate. It doesn't have to be completely accurate, but at 3.3 for the high value and 0 for the low value. So we're interested in the TTL output characteristics and the low voltage CMOS input characteristics, because the low voltage CMOS is the receiver. Just by the way, I've defined the problem. So let's see. So we'll just draw those on here. The input low for the low voltage CMOS is 0.9 volts, and the output input high, couldn't do that one, is 1.8 volts. So input high, worst case input high is, that's worst case 1 is a 1.8, worst case 0 is 0.9. And now we can look at the TTL characteristics, the output characteristics. 0.4, it's worst case low, so VOL. 0.4. VOH is 2.4. So voltage output high, worst case 1 on the TTL is 2.4 volts. And so we can look at this and first sanity check, 2.4 volts, worst case. Yep, that'll fit within the range of the low voltage CMOS circuit. So here's our LV CMOS and here's our TTL. And then we look at 0.4, see if that one would be correctly detected as a 0. Yep, that fits within the range. And so now we can figure out what the noise margins are. Well, noise margin high is going to be voltage output high minus voltage input high. It's equal to 2.4 minus 1.8 volts, 0.6 volts. Noise margin low is going to be voltage input low minus voltage output low. In this case is 0.9 minus 0.4 volts, and we get 0.5 volts. So these noise margins are positive, and as we sanity checked before, in fact, those would be received and allow for 0.6 volts and 0.5 volts of noise on the respectively high and low ranges. Okay, so let's look at another example. Let's suppose that the low voltage TTL gate, so we have an LV TTL gate, trying to drive a CMOS gate. Let's see if those ones would work. So our driver is the low voltage TTL, LV TTL, and the receiver is the CMOS gate. So we're interested in the output characteristics of the low voltage TTL and the input characteristics of the CMOS gate. Okay, so we'll draw these here. We have low voltage TTL, the output characteristics, nominally 3.3 volts to 0 volts, and CMOS nominally 5 volts to 0 volts. Low voltage TTL, worst case voltage output high, worst case output high value is 2.4 volts, and worst case output low, VOL, is 0.4 volts. For our inputs for our CMOS, worst case input low is VIL 1.35 volts, and worst case input high is 3.15. Okay, so we do a sanity check and we say, okay, this 0.4 worst case output, can it come across and be received with some noise margin as a 0? In fact, no problem. That one looks good. And then we do a sanity check on the high level on the 1 and say, can a 2.4 volt come over and be received by a CMOS as a 1? No, in fact it can't. It's in that middle region called the forbidden zone, where it's not detected as a 1 or a 0. So to write the equations, we can also do that and say, okay, what are the values that we would have for our noise margins? Well, we can do the noise margin low. We know that one worked, so we can try that one first. Noise margin low is equal to voltage input low minus voltage output low. We get 1.35 minus 0.4. So we get almost a volt of noise margin on the low end, on the zero end. That looks good. That would work. On the high end, we get noise margin high is equal to voltage output high minus voltage input high. We get 2.4 volts minus 3.15. And so here we have a problem. We get minus 0.75 volts. So we have not only no noise margin, but a negative noise margin. And as we saw with our thought experiment here, a worst case output high, a worst case 1 from the LVTTL driver would not be received as a 1 on the CMOS input. In fact, it's in the forbidden zone, in the forbidden region. So here's a case where we would try to run this circuit and it would either fail or fail intermittently, and we haven't done our homework or haven't done our research on making sure that these chips are compatible. One thing to note too, on this case as well as on the case we just looked at, is notice that this driver is also outputting up to 5 volts, so we have to make sure that in this case, LV-CMOS circuit could tolerate the high voltage levels as well. So even though the noise margins worked in this case, we need to make sure that in fact the 5 volts is not going to fry the chip. In this case, because the noise margin on the high end was negative, these chips are not compatible. They can't operate reliably in this configuration. So it only needs to fail on one end, the high end, and or the low end. It doesn't have to be both. Just one of them can make the configuration of driver and receiver fail. So because of the negative noise margin on the high end, this configuration of a LVTTL driver and a CMOS receiver does not work.